Hello. Today we will continue talking about the mathematical modelings, or the mathematical models or system models. Well, as we explained the last class, mathematical models or system models um, are needed in order to relate the input and the output, right? So in order to analyze control systems, mathematical models are needed, um, or mathematical models are needed of the elements used in such a systems. These are equations representing the relationships between the input and the output of a system, as we mentioned before. And the basis for any mathematical model is provided by the fundamental physical laws governing, in this case, the behavior of an element. Um, Saying that, there are different systems we as engineers that we use in our daily basis, and the systems are composed from mechanical, electrical, thermal, and fluid systems. These are the basic or the general systems that we can find in all the systems, specifically in the industrial sector. And this is how important it is to classify the mathematical models in order to um, to work with them and understanding to control the variables in the near future based on the type of design that we're looking for. Okay, so mathematical modeling of system models, right, are basically classified in mechanical, electrical. We have thermal models too, related to heat, thermal, and fluid. So now, as we know, based on the course outlines that we are working this semester, what we are really focused on is either uh, chemical related models, right? And the reason is because most of the times these systems actually have components of mechanical and electrical. That always happen. So once we analyze the thermal and the fluid, we also will be able to manage a little bit of these two. Okay, so but saying that, uh, I would like to just illustrate to you a little basic model related to fluid systems, and here is because uh, once we understand, we will be able to start to relate it to how to control it. Okay, so sometimes we find in the literature that we will find fluid systems or fluid system building blocks. Okay, fluid system building blocks or fluid models. Okay, so what happened here is that if we're thinking about a block, right, or a box where we have the fluid system, and or we building the fluid system block to make it more easier, and we know that we have input and output. Okay. Here, if we're talking about a fluid, normally what we illustrate here is the volumetric flow rate, or volume, right? Or rate, or volumetric flow rate. And what is the output? Well, normally, if it's a fluid system, let's say it's closed system or open system, depends on the application. What we will have has an output, has, I say, depends on the application. We can have like a pressure difference. Okay. So now, because because of the nature of fluid inside a system, we have different analogies. Okay, and that different analogies can be related to electrical systems, right? So when we mention the analogies related to electrical systems, or the analogies or similar to electrical systems, right? So what we're saying is that the equation equivalence to, for example, hydraulic resistance is similar to how electrical resistance behave. For example, if we're talking about for fluid systems related to hydraulic resistance, right? So what we will understand here schematically, so we have a pipe, and later we have a kind of valve, right? And the valve can go up and down, depends the type of valve, right? And we have, if we want to measure the pressure difference, pressure 1 and pressure 2 has an output, right? Pressure 2. Okay. So another schematics of that is this one. Is a reduction. So pressure 1 and pressure 2. So what do we want to say, or what is the meaning of hydraulic resistance? As we see the graphics here, hydraulic resistance is related to actually there is the resistance to flow which occurs as a result of a liquid flowing through the valves that we observing, or in related to the pipe is the changes in a pipe diameter, for example. So the relationship between the volume rate of flow rate of a liquid, that we can call it Q, has a flow rate, through the resistance element, that is the valve, and the resulting pressure difference, that is the variables that we are measuring in order to understand what is the value of that difference, right? So in this case, the value of that difference is simple as pressure 1 minus pressure 2. Okay, so now pressure 1 minus pressure 2 is equal to flow rate. So if we don't have no resistance, then we can apply this relationship as it is. But because the conditions are changing, so here are changing and here are changing, So we can have pressure 1 minus pressure 2 equal to flow rate, but now we have a constant that is related constant of hydraulic resistance, right? Related to this, a constant. The bigger the resistance, the bigger the pressure difference. So the bigger the resistance, the bigger the pressure difference. Okay? For a given rate of flow. And this is how we represent a very simple mathematical representation or model related to fluid systems, and just for this case is hydraulic resistance.